Please welcome Neil Olivier.
Time at the 2021 ACE conference. My name is Neil Olivier. I'm the Director of Corporate Services at NuScale Power. And I'll be taking you through our journey to implementing Aras PLM. Little background on me first is I'm not a PLM expert. I'm not an IT expert. I'm actually a nuclear mechanic at heart. I'm a knuckle dragger. I was on a submarine in the Navy for 7 years, and then moved on to commercial nuclear power, where I was an equipment operator at San Onofre Nuclear Generating Station. I was licensed at Columbia Generating Station up in Washington as a reactor operator, and then senior reactor operator and control and supervisor at Limerick Generating Station outside of Philadelphia. I came to NuScale because I'm very excited about the technology, and we'll talk about the technology and how we're using Aras PLM to help us get to the end goal of getting a small modular reactor built and in the ground and producing power. But also, I'm from Oregon, and so I came back to NuScale Power, or I came back to Oregon and worked at NuScale, and I took over our performance improvement program. And then eventually, as the Director of Corporate Services, we administer a lot of what we call NQA1 programs. They're regulatory required programs, such as the Corrective Action Program, the design program or reactor design program. And then also, and I administer them, I don't run them, but I make sure we meet regulatory compliance. And then I have a couple other departments too, but one of them is document control records management. And so it led us down the PLM journey. And I'll just give you a little bit of a background here, how I ended up, implementing the PLM program or implementation of Aras PLM is we had a records management software that was separate from our doc control software, which was actually a legacy PLM system. And I realized as I took over all these different systems that they were all disparate databases that pointed to each other, but nothing was integrated. And we needed to fix that. And so I actually went to a conference for PLM and saw someone talk about ripping out their legacy PLM system and installing Aras PLM. And I got intrigued, and so did my peer at work that was with me. And this was in 2018, I believe. And we ended up talking to the folks at Aras and included them in an RFP proposal, or a request for proposal for a fully functional PLM system. And we'll get into that later about why we chose them. So that's how we ended up moving to Aras PLM. So let's get started. I'll start on talking about our technology, and then we'll get to PLM related information. So NuScale, if you don't know about NuScale, our mission is to provide scalable, advanced nuclear technology for clean technology for the production of heat, electricity, clean water, hydrogen, to improve the quality of life for people around the world who don't have access to it. And we can achieve this by providing technology that's smarter, cleaner, safer, and cost competitive. We'll get into all those things here shortly. It's a smarter energy. It's flexible. Design can support multiple applications, such as hydrogen production and heating steam, electricity, and we can provide those to mission critical facilities because of the base load high production power that we have, but this clean energy is 100% carbon free, just like wind and solar, with a smaller land footprint, and we're safer than traditional nuclear, and that we don't need any AC power, we don't need any operator action, we don't need any extra water. So we eliminate those risk factors that impact nuclear plants, when they encounter events such as like Fukushima. So cost competitive, NuScale is far less complex than any other nuclear design. Our offsite fabrication assembly reduces cost, and we're ready to install when they're delivered on site, and therefore construction is shorter and more predictable. And we'll get into that a little bit later in depth. So who's NuScale Power? We were formed in 2007 for the sole purpose of commercializing an SMR, the NuScale Power Module, as we call it. The initial concept has been in development and testing since 2000. And Fluor, the global engineering and construction company, we call it a EPC, became our lead investor in 2011. In 2013, We won the DOE funding award. They gave us over $400 million in matching funds to develop this safe new technology. We have over 560 patents in 20 countries. We have over 400 employees in 5 different offices. And we recently, in 2020, got our NRC design approval, and that is the first for a small modular reactor. And so total investment to date is over $1 billion. And you can see there, we already have a functioning control room simulator at the bottom, and it's far different than any other nuke plant that I've worked at, in that it's much more advanced and intuitive than the old 60s design plants. So here's a a graphic that depicts our journey to commercialization, and it is an uphill climb because as everyone knows, there is, I would say, some hesitance to endorse nuclear power, but it really is the only way we're going to, I believe, get to our clean atmosphere or clean energy goals. So you'll see there that in 2020 we got our design approval, and we've been moving up this ladder for the last 12 years. But next up is forging and fabrication, and then hopefully in 2022 we'll get standard plant design complete and approved by the NRC and move on to construction and actually getting a plant in the ground. So why is it smarter? You'll see here, this is what I used to work on and operate is a typical pressurized water reactor. And there's 2 kinds of reactors in the country. There's boiling water reactors and pressurized water reactors that are in commercial operation today, about 100 of them. This one, the pressurized water reactor type, is the one that's like San Onofre. Inside these large dome containments that have thick concrete walls, you have a reactor pressure vessel, pressurizer, steam generators, and reactor coolant pumps, and none of these components are small. They are very large. But with our design, you can see we remove the need for external pressurizers and steam generators because they're internal to the design. And then we also, since we use natural circulation, we remove the need for reactor coolant pumps. What you end up with is a very compact containment and reactor pressure vessel that is about the size of a traditional core and reduces the size immensely. And you can see here the containment vessel encloses the reactor pressure vessel. It's all in one integral unit. It includes the steam generator and pressurizer and containment in an integral package. It produces about 77 megawatts of electricity per module, but they're small enough to be built in a factory and transported. And you can dedicate each one to whatever independent operation you want, whether or not it be you want one of 12 modules to produce heating steam, one of them to produce hydrogen, or all of them to produce electricity. You can get up to 12 modules with 924 megawatts of electricity, and down to 4 and 6 module plants, depending on your needs. So if you want 12 modules, you can scale up to that and be close to the traditional nuclear power plant, the large scale power plants, but a much smaller footprint due to our design, our safe design, and get close to that same megawatt electric output. So in comparison to the large scale pressurized water reactors, you can see here, and I showed you a pictorial before, the containment module is about the same size or a little bit larger than one pressurizer. And there's many components inside that large dome. So our footprint is much smaller with that tighter package, essentially about 1/100th, I believe, or you could fit 100 of those containments inside a large scale facility, but we produce 10% of the power. And so why is it safer? We'll get into that. So you can see the module there, and we've talked about the output of the SMR. They sit inside a bay of water inside the reactor building. This provides us with a triple crown of safety because the plant will shut down with no operator action or control room system action, no AC/DC power, and no additional water. This allowed us to end our emergency planning zone at the site boundary, which you can see in that pictorial. And this is an old diagram. It's about 34 acres within the protected area fence. A traditional plant, the emergency planning zone goes out beyond 5 miles in every direction. And I used to work in the control room, so I was responsible for notifying those areas in case there was ever an event of any type. to inform the surrounding public. We do not have to do that because of the high reliability of our design. So why is it so safe? Because we don't rely on pumps, electricity, we rely on gravity. And so you can see here, this is a pictorial of one reactor or small modular reactor that is inside the pool. You can have up to 12, but the pool is sized to allow for adequate decay heat removal over an indefinite amount of time during a shutdown. So an emergency shutdown, rods go in, the decay heat removal system turns on and starts transferring that decay heat. Now, decay heat, if you're not familiar with the term, it is similar to an electric stove. If you remember those old school burners, couldn't put your hand on it the minute you turn it off, you'd burn yourself. Well, a reactor produces decay heat over a lower over time. And you can see there at the bottom, it says 1 second, we're still producing 10 megawatts thermal, and in an hour, it's 2.2. We're basically removing the heat from the residual heat. And over the course of 30 days, you will lower the heat so much that beyond 30 days, you can be air cooled. And so we need no extra water in the pool. We transfer all that residual heat to the pool, and we can, the plant is walk away safe. You don't have to have operator action, unlike any nuclear power plant that's been designed today. And we've talked a bit about this. We'll kind of go over a little bit over the stuff. But so the way we remove the heat during power production, and we use that heat to spin a turbine and make electricity, is through conduction. And the water's heated, the nuclear reaction transfers heat through the walls of the tube walls of the steam generator. The water is heated by convection, and then due to the increasing temperature of the water and gravity and buoyancy, the cooler water falls, the hotter water rises, and we create natural circulation. There's no need for pumps. So we naturally remove the heat from the fuel and transfer it and make steam, and then we can use that steam for various things like electrical production or for heating steam or hydrogen production. The defense, and that allows for a defense in depth that has never been done before, because we need no electricity to, one, transfer the heat away from the fuel, but in an emergency situation, it allows for no requirement of electricity. And so we have a second to none safety case, and the site boundary, like I said, is now the emergency planning zone is now at the site boundary. So why are we cost competitive? And this is where really, NuScale, the rubber hits the road. Why we make sense is that we are going to fabricate the power module all the way out to containment in a factory. That's never been done before. We'll get into the problems with traditional nuclear construction and why they have cost overruns, is because, frankly, you can't control costs because it's harder to control quality out in the field. You can imagine welding out out in some type outside. That's where all the fabrication is done for a traditional nuclear power plant. They do what they can to mitigate it, but it's not a factory where you control things like an assembly line, and you can control quality. So we will build them in a factory. The module will then be shipped by truck, rail, or barge to the plant site and basically installed. There'll be very little fabrication on site for the safety related portions of the plant, and then it'll house them in a 12 module reactor building or up to, and create that low carbon, secure electricity, that base load power that we're missing right now. And the only thing making base load power, if you're not familiar with the term, is coal and hydrogen and nuclear. And the only one that's zero emissions is nuclear. And so that's why I think we'll be successful. So how do you maximize the benefits of repetitive, or what are we doing to maximize the benefits of repetitive factory fabrication? We engaged BWXT Technologies. They selected in 2018 to be our lead manufacturer in fabricating the power module. They're very experienced. They've been building reactor pressure vessels and submarines for a long time, and we're collaborating with them to optimize our design for manufacturing and transportation so we can further reduce the cost of the NPM. And then Doosan Heavy Industries was engaged in 2019 to support our worldwide effort. So here's a little some information on historical nuclear construction, which will lead us into why we need PLM. So traditional nuclear power plants are immensely complicated. You can see in the picture they can take up to a decade to construct. And for those of us that are old enough, remember the 70s and 80s, we had 3 Mile Island, and the focus was on nuclear safety and increasing efficiency, capacity factor, and safety. And largely the nuclear industry has the highest capacity factor. That means the largest percentage of time at full power of any source of electricity. And we did that through lots of design changes, equipment upgrades. We changed our process, our training, and all of these were driven from regulatory requirements. But after years and years of design changes, resulting in many plants losing the fidelity of their original design requirements. So what I mean by that is we incrementally changed all these plants, but the initial final safety analysis report, that's the report that said these are all the requirements. This is the list of requirements that you must meet at all times in operations, or you have to do something to compensate. They lost that fidelity and could not prove to the regulator over lots of design changes that they met all those requirements. And so it resulted in, not every plant did this, but some plants had to do a design reconstitution, which was a lengthy and expensive engineering process to validate that your current model or modified plant met its original safety case. And so this is what we're using PLM for, and this is the problem we're solving, is controlling requirements. So all that our SMR design is vastly, it's a lot simpler and safer. There's still 60,000 requirements that need to be maintained. We need to prove that we can maintain. And so legacy plants have struggled because all that information has been document based. We used to joke in the 80s, in an old anecdotal story, that they used to back the constructor, when we turned the plant over to the operator, would back up a truckload of paper, and you had boxes and boxes of paper, and they say, okay, here's all the information about your plant. But it's hard to maintain all those design requirements when they're in volumes and volumes of paper. Well, fast forward, to 2000, the 2010 timeframe, and we started constructing, 2 large-scale facilities out on the East Coast. They're still managing things in a paper-based way, but in a digital form. So in other words, now we have PDFs versus paper, but they're all in disparate systems. And so we needed to come up with a new way of doing things. And we kind of looked at the way the aviation industry does it. So these legacy plants, they have found a way to maintain their design basis, but it's not efficient. And so, one time I sat in as a senior reactor operator and control room supervisor. I was the last line of defense to in turning mods back over from engineering and maintenance to the operations department, putting them in service. I'd have to dig through mountains of paperwork to validate that those system upgrades still met the design basis requirements. And I remember talking to an engineer who had to go outsource a safety-related heat exchanger, and the amount of time he spent trying to figure out that he'd gathered all the right requirements, it was immense. I felt bad for him. And then me validating it was a little tricky, because I was like, okay, I had to be sure that he did his job correctly, versus having a system where I could just trace all the requirements back to their the component, trace it back to their base requirements. And that's our goal. So, nuclear power plants have always struggled because they've all been individually engineered projects, large projects, and ours is going to be modular, more akin to, I would say, the aviation industry, and managing those requirements and those design differences in concert in one system. Excuse me. So managing requirements from design to decommissioning is the goal. So those design requirements come in many forms: regulatory statements, code requirements from ASME, bounding parameters, custom requirements, or site-specific requirements. If you design a plant that's bounding, but the area that it's in is different, there needs to be some changes to the plant. A good example is a plant that operates in Denver at that altitude is completely different than one that operates outside New Orleans at sea level. There's different atmospheric requirements, and we need to change the design accordingly, but we need to track those again in one holistic system. So those design changes can come, and future design changes can also come from the federal government. The customer can change those design requirements, or an industry initiative, or just out of plain necessity. So we need a platform that allows us to apply system engineering principles and drive those requirements from any part in the BOM with clear traceability back to the base requirements. And we need to maintain configuration management of that design, whether the design change occurs next year, 2029, or 2089. If you've noticed, due to necessity, there's a lot of power plants that are operating when they were originally designed for 40 years, sometimes 20, and now they're operating 60 and 80, and they've gone through and done this upgrade projects. We plan on our design lasting a very long time, and so we have to maintain configuration management of that. So there's that paradigm shift that we're going to be the first nuke power plant to be designed and managed the requirements by PLM as the backbone for our single source of data. This will allow configuration management of multiple iterations of the same design, but ensuring we always meet original design requirements, regardless of the variation or design change. The licensee, and that's what we call in the nuclear industry an owner and operator of the plant, will receive a digital twin, and with all the relevant design information instead of a truckload of, I call digital paper, or disparate databases of information. The application of the digital twin will make the design requirement traceability and changeability down to the part. And Aras PLM is going to allow the owner to consistently manage those configuration changes, or whoever the owner puts in charge, because some owners don't manage them. They have a design firm that does, across the entire life cycle of the plant, maintaining that license basis and final safety analysis fidelity long term. So in the beginning, I talked about how we came to Aras PLM, but once we made the decision to go to Aras PLM, we had no less than probably 7, 8 databases of information, and we needed to come up with some implementation goals. So this is what my team came up with. So minimize the use of multiple software suites, multiple workflow engines, and databases at NuScale. So we create that central data repository that's able to relate information in a way we weren't able to with those disparate data and software solutions. We need to take advantage of the automation provided by Aras PLM with the end goal of minimizing paper procedure usage and maximizing automation, but still enforcing those stringent process and quality requirements that are required by the Nuclear Regulatory Commission and frankly, what we should be doing. We should have the highest level of confidence in our design. So we want to use simple, repeatable workflow designs to drive a sustainable increase in user efficiency. One thing I may have forgot to mention is that, and I meant to say this at the beginning, if you have questions, please enter them in the Q&A session, and I will be getting back to you via email. And so whether it be about our technology or about PLM, I'm just not going to have time to answer them, but I will get back to you. So I'm not ignoring you. Just wanted to make sure you knew that. I forgot to say that at the beginning. So this is a key point also about getting back to the repeatable efficiency, or the repeatable workflow designs and how to increase efficiency. Every single system we had, you'll see all the functions we had somebody different develop the workflow for processing that data. And it was mind-boggling to me when I ended up with a majority of them under my administration. I couldn't believe that something that had so similar a function was built completely differently. And what did it mean? We had multiple different training sessions to try to train users on all these different workflows when we could have used the same, at least similar design, so we don't have to retrain our workers. So that's our goal, is to retool all those eventual workflows so that they don't have to be trained on every single workflow. They'll know how it's supposed to operate. And then, the end goal, and this is the most important, is that we get the right data to the right user at the right time. It was hard to get information out of PLM and correlate it with stuff in records management and all the different other functions that we have. And then lastly, we need to create a scalable, flexible system that's qualified for records and data storage so that I can prove to the regulator, the customer, that we're maintaining our requirements and our design. So these are the functions we attempted and are absorbing into PLM in phase 1, document and CAD management, our requirements management, records management, and corrective action program, which is regulatory required along with design control, design impact analysis, open design items, record retention, controlled document access, signatures. I add that in there because we were using Adobe Signatures, which meant a lot of passing of documents via email and stuff, which we're getting away from. And then actually configuration management of the digital software. We're going to use Aras to manage at least the records associated with our software configuration management program. So a couple of these have been postponed to phase 2. Corrective action program is pretty much the only one, actually. And the rest are all been in phase 1. And it was a long project. It was 2 years. And you can imagine I had a different workflow or database system for every one of these. And it was a lot of lost efficiency pushing data between systems because a lot of it was manual. And so this gets to the heart of the question is, why did we choose Aras Innovator? We already had a PLM system, but it was not user-friendly. But when I talked to folks that had moved from a legacy system to Aras, the flexibility and the scalability is some of the things that caught my eye, and I decided that we should give them a chance. Their unique architecture adapts to changing processes versus software that forces you to adapt your process to the software, and I didn't want to do that. And so with Aras, we realized that the digital thread could come sooner at lower cost, and it could transform with NuScale. As our processes change, the system is easier to change to meet our process needs, and that's going to happen. Regulatory requirements change. We have to do certain other things, and so we need to have that flexibility. And so scalability was another one. The cost of our legacy systems was higher than the fully functional PLM system that Aras has, let alone we still needed other modules for our legacy system that was going to balloon costs per user, and we couldn't justify it. But with Aras, it supports those increasing demands with their subscription structure. And so we wouldn't have been able to do that under a traditional licensing structure, software licensing structure. And then a big one was upgrades. And if anybody's familiar with it, Aras guarantees those upgrades. Our legacy system, we would frequently break workflows every time there was a major upgrade. And so Aras's unique architecture enables the system upgrades without disrupting our custom functionality. And since those upgrades are guaranteed at zero cost, it was easy to prove why this was such an upside to our execs. And so historical upgrades have cost us $100,000 per upgrade, and that's just the cost of the vendor who is doing them for us. The repeat retooling of workflows wasn't even factored into that. And then tool agnostic, Aras allows NuScale to manage all our tools and databases in a way we couldn't have done before. A good example is CAD. We've switched between multiple CAD systems, and then on top of that, we have suppliers and customers who use different CAD authoring tools, and we need to be able to manage those files in concert. And so my attempt is to future-proof NuScale, and that if we needed to switch CAD from, say a SolidWorks to NX or NX to CATIA or something along that line, that we'd be able to roll those punches with the minimum impact. And so in closing, what we're intending to do with Aras Innovator is manage all our design requirements, house all our quality and non-quality records. And I didn't really get into that, but we're using it for all records, managing our design changes, and we'll eventually manage enterprise change, automate all our engineering workflow tasks, CAD management, BOM management, future simulation management, future maintenance, repair, and operation data management, and virtual design reviews. My long-term goal is to be able to allow an engineer to slap on an Oculus type device and walk through the plant and point out, hey, this doesn't meet design requirements because now I can see it, and I can see this fire pump's too close to this wall, things of that nature. Before we start construction, which has been a legacy issue with new power plants, is the location of equipment has not always been understood because it's in some engineer's mind and it's on a drawing until you get a valve you have to operate it. And I'm a victim of this as an operator, that every time we shut down the plant, I have to build scaffolding 40 feet in the air because an engineer put a valve that routinely has to be operated with no way to get to it. We could see those types of things. That's the long-term goal. And so just say when performing our selection for PLM, for a PLM platform, if you look at cost, flexibility, long-term resiliency of the solution, Aras was it. and it was hands down the winner. So, and we went live 2 months ago, and I look forward. It's going to be exciting over the next few years to increase our functionality and maximize our use of Aras. So, thank you very much, and I hope everybody enjoys the conference. I know I am. Thanks.